The next is integration property. Again, we have this condition, this pair of Fourier transform. If we do integration in the time domain, then this will be what's happening in the frequency domain. So the original signal spectrum will be divided by j omega, and there's an extra term. Here is one example. Find the spectrum of xt, and we know that this x of t can be treated as an integration of a shifted rectangle signal. So we know that for the rectangle signal, shifted rectangle signal, its spectrum is a sampling function and then having a phase shift in here. And based on the integration property, the spectrum of the signal in here will be equal to the spectrum divided by j omega, and then plus the spectrum at 0 point times the delta of omega. So here is the result. Here is another one. We have very similar signal, but it has a DC component. So it will be a DC component 1 plus what we had in previous example. So using the linearity property, we can write out the original signal is equal to a DC component plus an integration of a shifted rectangle signal. So using what we had previously in the previous example and the Fourier transform of the DC components, we can reach these signals Fourier transform is equal to this spectrum. The next property is time differentiation. We're given a pair of Fourier transform, and if we do derivation in the time domain, then correspondingly in the frequency domain, the spectrum will be multiplied by j omega. We can use this property multiple times. So if we're doing the derivation in nth order, we do this n times, then the multiplication in the frequency domain will happen n times as well. In this example, we ask people to calculate the spectrum of the rectangle signal, but you have to use the time differentiation property. So what we can do is we can calculate the first derivative of the waveform, and here is the resulting waveform. It's sum of two delta functions. They are both shifted, and the spectrum will look like this. We can use the time differentiation property directly. So the original signal's spectrum will be this spectrum divided by j omega. And here is the result. This is the second example. We're asking people to figure out the spectrum for a triangle signal using time differentiation property. What we can do is, again, we can figure out the first derivative of the original signal, and these actually are sum of two rectangle signals. And we know this is a pair of Fourier transform, so that the spectrum of the first derivative will become sum of two sampling functions with phase shift. And then based on the time differentiation property, the original signal's Fourier transform will be this spectrum divided by j omega. So we get the results will be 4 times sampling function squared. What about this signal? If we use the time differentiation directly, we see the first derivative of the signal will be a rectangle signal. And if we figure out this spectrum, it is sampling function with a phase shift. And based on the time differentiation, then the spectrum of the original signal will be this function divided by j omega. However, we know in the previous example, the spectrum for this waveform actually is equal to this function, and there's an extra term in here. What is the problem? When we do the derivation in the time domain, any DC components will be lost. So that is the reason we can see there's some difference in here. So when we try to use the time differentiation property, we need to pay attention to the DC components, or we need to compensate for the DC components in the original signal. Therefore, we try to modify the time differentiation property. And here is the modified version of the time differentiation property. So if there's some direct current components in the original signal, then we need to have an extra term about delta function. So using this modified time differentiation property, we can try to redo the previous example. So the first derivative of this waveform is a time-shifted rectangle signal, and the spectrum can be figured out like this. Now we use the amended time differentiation property. We can get the answer like this, and we put all the values in. This will be exactly the same as the previous example. The next property is frequency differentiation property. So based on the duality we learned previously, if we do the first derivative in the frequency domain, then we're going to do the multiplication in the time domain. But there's a sign change in there, and you can put the negative j on the other side of the transformation. So this will be the frequency differentiation, and pay attention to the correspondence. First derivative in the frequency domain corresponds to multiplication in the time domain. And we can do this multiple times as well. So this is also belong to the frequency differentiation property. Before we introduce the next property, we want to introduce one concept which is called energy spectrum of continuous time Fourier transform. Let's first figure out what is the energy of a given non-periodic continuous time signal. So this is the definition, and we can break the square into the multiplication of the original signal and its conjugate. Now introduce the inverse Fourier transform. We can rewrite the second term in an integral. And now we can try to switch the order of the integrals. We get this definition. It is a continuous time Fourier transform. And we put it into the equation, and it's clearly that the energy of the original signal actually can be calculated from the frequency domain as well. And we're going to define these is the energy spectrum. So the squared spectrum for continuous time Fourier transform is energy spectrum. Okay, now we can introduce the Parseval law for continuous time Fourier transform. So you can calculate the energy either from the time domain or from the frequency domain. They are always equal. And this is content for Parseval law for continuous time Fourier transform. We're going to see one example how we can make use of the Parseval law. And this example asks us to calculate the integral of this signal. If we look at this signal closely, we're going to find out this actually is the sampling function. And we know the sampling function and the rectangle signal actually is a pair of continuous time Fourier transform. So you may evaluate the energy either in the time domain or in the frequency domain. So now we can use the Parseval law to convert the integral of this function, of this signal in the time domain to the frequency domain, so that the value of this integral actually is equal to the integral of the energy spectrum. So it's quite easy to solve this integral in the frequency domain. Clearly, the result is equal to pi in here. So that will significantly simplify our calculation for this integral. Thank you.